Hi students, so today we start lecture 73 in our course on aerospace engineering, and today I'm going to talk about strain displacement relations, and at the end of this lecture I'm going to discuss the very important compatibility conditions for the strain state. I'm Dr. Ranjan Ganguly. So let us again look at the aircraft. We now know that at any given point there is a stress matrix associated with that point. We also should remember that at the same point there is a strain matrix which is associated with that point. Now, of course, you can ask the question which comes first, but my thinking is that stress comes first because you apply certain loads to the aircraft structure and therefore you get stresses, and then because of the presence of stresses you get strains. Now strains are of course related to displacement. We saw that in the basic definition of strain for an axial rod, but we can think of it in a more generalized manner, which I am going to try to let you to understand today. So we can look at displacement itself in this form. For example, let us set up a coordinate system x, y, z or x, y, z, and then let's look at a certain point P here. Let's say the point P can be represented by a vector x. So this is very simple case in any kind of vector situation because you are dealing with a three-dimensional coordinate system. You will have a vector x and you can represent the point P here. If you recall unit vectors in physics, you could say these have I, j and k components in the x, y and z direction. Now let's say this point has moved to some point P dash, and this is the displacement which has taken place for this particular point, and this point is in some solid. So what will happen is that at this point P dash, the displacement vector has shifted to x dash. And now we can define displacement formally. Displacement is a vector. This is x dash minus x, and it's got three components u, v and w. So u is the component in the x direction, v is the component in the y direction, and w is the component in the z direction. So it's very important to remember that displacement in general can have three directions: the x, y and z direction, and the displacement in each of these direction is given by u, v and w respectively. Displacement is therefore a vector, and remember that stress and strain are matrices, or some people like to say they are tensors, but then matrix is also a type of tensor, so that's something you can remember. Now in general we will have a concept known as a displacement field. So what happens is that at any point u is going to be a function of x, y and z. So you can clearly see that in a general structural system here, u, v and w are going to be functions of x, y and z. Therefore, of course, they are going to have partial derivatives with respect to x, y and z, and these are going to give you the rate of change of u with respect to x, the rate of change of u with respect to y, and the rate of change of u with respect to z, for example. So what happens is that these particular rate of changes are related to what is known as strain. So let's look at a typical displacement field. Now if we were to differentiate these displacement with respect to x, y and z respectively, then we will get these three values here. So epsilon xx is du by dx, epsilon yy is dv by dy, epsilon zz is dw by dz. Now some people use the term dou to segregate this from the actual d which is used in the normal derivative or the ordinary derivative, but I am simply using d here because it's obvious to you that these are partial derivatives. So we can see that physically the values which are there for normal strain represent the rate of change of displacement along that particular coordinate. So epsilon xx is the rate of change of u along the x direction, epsilon yy is the rate of change of v along the y direction, and epsilon zz is the rate of change of w along the z direction. So here the presence of the subscript tells you that there is a x here and a x here. So there is a u here and a x here. Both are in the same direction here because u is also in the x direction. U is the displacement in the x direction, v is the displacement in the y direction, and w is the displacement in the z direction. Now let's look at the somewhat more complicated case of shear strain. So in shear strain what happens is that you get two partial derivatives here, and these derivatives correspond to the rate of change of displacement along the other coordinate direction. So what happens, for example, if we take gamma xu, or rather gamma xy, we have the variable u here and v representing the displacements in the x and y direction, and we differentiate u with respect to y and v with respect to x. So this is like a cross derivative, and what this is telling us is that the shear strain in the xy direction corresponds to the u displacement differentiated with respect to y and the v displacement differentiated with respect to x. Similarly, if you see the xz case, you will have u and w here which are in the x and z direction, and you will differentiate with respect to the other coordinate. So that u gets differentiated with respect to z and w gets differentiated with respect to x. Similarly, if we look at gamma yz, we have the v and the w coordinates in the y and z direction, and the derivatives are with respect to the other displacement here. So v get differentiated with z, which corresponds to w, and w gets differentiated with respect to y, which corresponds to v. So this is giving you the definition in terms of the displacements and the strain. So these are also sometimes known as the strain displacement relations. So let's write all these equations down here. So there are 6 of them. So we can see that the 3 normal strains here, which I have given in blue, they are the direct differentials here with respect to u, v and w, and being differentiated with respect to x, y and z. And as far as the shear strains are concerned, these are the cross derivatives here. So again, that's something which I explained in the previous slide. Now we can put this in the matrix form. So it looks nice now in the matrix form. So you can clearly see that as far as the strain is concerned, if you have the displacement field, that is the variation of u, v and w with respect to x, y and z, you can very quickly obtain the strain matrix for any given displacement field. So let's do this example to cement this concept. Let's take u, v and w. Let's say this displacement field is given in this manner such that u is 0.01y, v is 0.02x and w is minus 0.01z. Now I have the strain displacement relations in this matrix. So let me try to get these particular values. So what happens is we can take, let's say, the first one, du by dx, that's simply 0 because this is with respect to y. So if I differentiate u with respect to x, that's going to be 0. So I get 0 here. Du by dy, that's of course 0.01. So I get 0.01. dv by dx, that's 0.02. So I get 0.02 here. Du by dz, that's simply 0 because there's no z in this u equation. So I get a 0 here, and dw by dx, that's again 0 because there is no x in the w displacement field. So I get two zeros here, and here I get dv by dy, that's again 0 because there is no y in the v displacement field, and dv by dz, again it's 0 because v is not dependent on z. dw by dy, again that's 0 because w is not dependent on y, and dw by dz is minus 0.01. So that's something which we can differentiate and get. So now once we get these particular values, we can very easily write the strain matrix here. That's going to be 0, 0.03, 0, and of course it's a symmetric matrix. So I will have 0.03 here, and then I have the epsilon zz given by minus 0.01. So you can clearly see that if you are given a displacement field, you can get the strain field. Now, of course, if you are given a strain field, you can also get the displacement field by integrating, but you will also get a constant value there because integration throws back that constant towards you. Now, in most cases, if you are dealing with simpler problems such as plane problems, plane stress, plane strain, and so on, then the matrix becomes smaller because the z direction can be ignored here, and therefore you have the situation where epsilon xx is du by dx, epsilon yy is dv by dy, and gamma xy is du by dy plus dv by dx. So one of the things we can easily prove for the plane condition is the compatibility conditions, which essentially relate the shear strains and the normal strains. Now this is more difficult to show in the three-dimensional case. It's simply more algebra, that's all. But we can get the concept from this particular case. So let's say you are sitting with this equation here for shear strain, that is gamma xy is du by dy plus dv by dx, and maybe you are looking at it on Saturday night, you have nothing to do, so you decide, let me try to differentiate this with respect to x. You do that here, you get this derivative here. So what I have done is differentiated gamma xy with respect to x, the du by dy with respect to x, and dv by dx with respect to x. Now you say, okay, I did one differentiation, let me now differentiate it with respect to y. So you do that. So you differentiate this with respect to y on both sides. So what you get is this equation here. So here you have the dx dy term. Here you have the dy square dx term. Here you have the dx square dy term. So you get this equation. Now, of course, here I am assuming that the fields here u and b are differentiable. So that's something which permits me to differentiate these particular equations. Now if we look long and hard at this equation, you will clearly see that du by dx is epsilon xx, so I could make a substitution here, and dv by dy is epsilon yy, so I could make a substitution here. So if we do that, then I get that the second derivative of gamma xy with respect to dx dy is equal to second derivative of epsilon xx with respect to dy, and the second derivative of epsilon yy with respect to x square. So this equation, which is known as the compatibility equation, relates the derivatives of the shear strain to the derivatives of the normal strain, or we can even say that it relates the shear strain to the normal strain. So we cannot say that we can have any arbitrary displacement field in problems, or we can have any arbitrary strain field in problems. We should have fields which satisfy the compatibility conditions, because that's going to work out much better, because these aspects of differentiability will be satisfied there. Now if you look at the more general problem, you will find that you will get several equations for compatibility, because they will also involve the strains in the z direction. If you look at many books on mechanics of materials, such as the advanced books, for example, there is the advanced structural mechanics book by Bodinas, then you are going to get the derivation of that. It's simply a matter of differentiation. So if you have some time during a weekend when you are feeling very bored, you can try to get the compatibility conditions for the full strain matrix in that case. That will certainly help you a lot down the road. So I'll stop this video now. In the next lecture, which should be the last lecture on the structures part of the course, we are going to look at one thing we have missed out till now, which is the equilibrium equation. And that equation is similar to the compatibility conditions for strains, which tells us that the strains have a relationship. The equilibrium equations also say that for a non-uniform stress state, the stresses also are related. So they are not totally independent. They are related in some way. And of course, they are related by an equation. That's how most things are related in mathematics and engineering. So I'll end this video now, and I will see you in my next lecture. See you then.